Okay, so in this lecture, we are going to cover several topics. There's not really an overarching theme, it's just several different sections that weren't covered from Artin last time. And so these are the topics: linear transformations, orthogonal matrices, rotations, differential equations, and the matrix exponential. So we'll start with 4.1. The analog for homomorphisms between groups is called a linear transformation. The analog to vector spaces is called that. And obviously you know that from linear algebra, which is like usually represented as T from V to W, where V and W are vector spaces over a field F. And there's two main properties to a linear transformation, in that we can separate addition out from the brackets and we can pull scalars out from the brackets of the transformation as well. And this scalar is specifically in the field. Also, linear transformations are compatible. Would I say linear transformations are also compatible with linear transformations? That's not right. It should say something else there. It's a typo. But this is basically a huge sum that we can do all at the same time, because it's a scalar being multiplied by a vector added up over a huge sum. And so this is just the same two properties here being applied over and over again. And you can prove it by induction, but we're not going to do that. By the way, there will be like exercises for some of these, but they're not big exercises either. So it's like exercises that you could do like typing in chat. So I'll probably stop at some point and be like, ask you guys a question, and you guys can like type up an answer or hop on mic or something. It's up to you. So yeah. An important example of linear transformations is obviously left multiplication by a matrix. And it's usually represented by this function here. And it's from f of n to f of m. So it produces a vector. And it's linear because these properties hold. This is from matrix properties. You already know this. Another linear transformation is the derivative function. So any polynomial with degree less than n, we can apply the derivative to it, and it will take us to the polynomial space of n minus 1 because of the power rule. And there's two spaces that we usually talk about when it comes to linear transformations. One is the kernel, and one is the image. And so the kernel is just any vector that goes inside the transformation and comes out as 0. It's every single vector that does that. And the image is just any vector that pops out of the transformation when you put in a vector. So it's every vector in that space that has an input, is the more rigorous way of saying it. And both of these are subspaces. These are usually like some of the first two subspaces you might learn about. And if we change the linear transformation, right? Because in the last slide, this was some arbitrary linear transformation. But if we change it to this one that we talked about earlier, we get something interesting, which is that the kernel is a set of solutions to ax equals 0, and the image is exactly the set of vectors that is the linear equation ax equals b. And so this leads us obviously to the dimension formula. I mean, the last slide doesn't, but this is also another important result of kernel and image spaces. Basically, the dimension of V can be broken up into the dimension of the kernel of the transformation plus the dimension of the image of that transformation, assuming that V is finite dimensional. And we actually call these numbers here the nullity and the rank of T. I think I had it backwards there. And the proof of this is given in the textbook. We start by letting the dimension of V equal n with a basis of u1 to uk, so all of these are vectors. And if you're wondering, this is the notation for... oh, by the way, can you guys see my cursor? Like, I'm like highlighting this bracket. Okay. It just means that this is an ordered set, I believe. This is the notation for an ordered set. So we start with a basis for the kernel and extend it to a basis for V, because the kernel is smaller than V, right? So we end up extending it by some amount of vectors, n minus k vectors to be exact. And then we define a transformation, wi equal t of vi. So this is all of these v's. We take the output of them from the transformation. And all we have to show then is that that output is exactly n minus k. Because if we had a basis with k vectors and we extended it by n minus k, and that's a basis for v, then we're basically arguing that k vectors plus n minus k vectors adds up to exactly the dimension of v. And so that's basically the gist of this proof. So if we can show that these vectors, the wi, is a basis for the image, then we're done. And so that's what we end up doing here. We let S be these vectors, ordered, w1 to wn minus k. And our goal is to show that the spanning set of these vectors is in fact the image of T. And that it's linearly independent. We want to show that it generates it and it's linearly independent, because those are the two properties of a basis. And to start, we note that clearly the spanning set of S is a subset of the image of T. And we'll come back to that. I'm actually going to ask you why at the end that is kind of clear. So we're going to prove the reverse direction. And so we'll take some vector in the image of T. And we know that if it's in the image, then it equals some input vector in V. And we can rewrite that in terms of the basis vectors from before. If you remember in the last slide, we said that, well, we're going to let this be a basis for V. And V is obviously in V, so we can write it in terms of scalars like this. And so we apply T to both sides, right? And we actually get W over here, because we said that W was the output of T of V. And we get a bunch of zeros here, plus B1 times the output of each of these V1 all the way up to Vn minus k. And the reason that we get 0 over here is because this ui, this vector here, is part of the kernel, right? We said that this was a basis for the kernel. And we know that anything that's in the kernel will get sent to 0 when we apply t to it. So we end up with w is equal to 0 plus all of these. And that is exactly what it means to be in the spanning set of S, because remember we defined it up here. So yeah, that part is relatively straightforward. The next part is to show independence. So we start by assuming that this relation here, this linear relation, equals 0. And we want to show that each of these CIs here must also be 0. So we consider the corresponding linear combination that we get from substituting in each of these w's for this equation right here, right? So we'll let V be whatever this is. Each of these VIs that send to each WI, we let V be the linear combination of them. Well, if we apply T to this, right, we get this initial expression here. And we know that that equals 0 because we started with that. We assumed it. So then that means that V must be in the kernel of T because it gets sent to 0. And so since V is in the kernel, we can rewrite it using the basis vectors, which are all of these U's from before. And we can substitute it back into our equation with CI. And that equation was back here, I believe. No, sorry. Oh no, yes, sorry, we plugged it in here. We plugged it in here. We brought it to the other side. And we get this long bunch of negatives plus this huge amount of this huge linear combination. And we know that this linear combination is part of the basis, right? That we already assumed was a basis. All the way back at the start, if you remember. It was this huge basis we set up for V. And well, if that is a basis, then all of these have to be 0, which includes all of the C's. So that means that this equation here at the start has to be linearly independent. So since this list of vectors is linearly independent and the spanning set generates the image for T, we must have that this is a basis. And so because the size is n minus k, that's exactly what we wanted to show. And so my question to you would be, why is it obvious that the spanning set of S is a subset of the image of T? And I'll let you think about this. And I'm curious to hear what you think. You can like type in chat or do whatever, but why did I basically gloss over that? I can roll back the slide too if you would like. Yeah, right here. We wanted to show that they're equivalent. And I kind of glossed over. I said, oh, this is obvious. Which I don't like doing, but... Okay, let me read the chat. Yeah. Yeah, no, I think what you're saying is right. Yeah, yeah. I think I phrased it a little bit differently, but yeah, that's basically the idea. Is that each of those WIs are literally part of the image, right? And I think I wrote it in the next slide. Yeah, we can write S as like literally those image vectors. And so any vector in that span can be rewritten in terms of some linear combination. Yeah, that's exactly what you said. Yeah. Yeah. I think I wrote it this way so that you can see the actual vector that creates W for any W in this spanning set. But yeah, because it's a subspace, it has to be part of the image. Okay. So next is orthogonal matrices and rotations, which is 4.5. I know we made a big jump. And so we're going to talk about how we can perform rotations on vectors. And previously, earlier in the book, they mentioned that one type of rotation is with the matrix in R squared, which is here. Cos theta, sine theta, all that stuff. And so a rotation in R cubed about the origin can be described as a pair v theta, where v is a unit vector of size 1, and theta is some non-zero angle of rotation. And so a matrix representing this through the angle theta of some vector, we chose E1 here, which is the standard basis vector. Here is a rotation through that angle that you would... Yeah, that fixes the first coordinate and rotates on the second two. We won't focus on geometry too much, actually, I think, in this section. But yeah, all rotations are linear operators. But the matrices can get more complicated the higher up you go. And so we define orthogonality, which is that a matrix is orthogonal if its transpose is equal to its inverse, or that the matrix itself times its transpose is the identity matrix. And you can form a subgroup of all of these called O of n, or just the orthogonal group, which is defined here. And so the determinant of an orthogonal matrix is plus or minus 1 because, well, if we multiply the transpose by itself and get the identity, we can take the determinant of A and break it up into two components. We can rewrite it. And this will equal 1, right? Because the determinant of the identity is also 1. So we will have that it's either plus or minus 1. You can have negative and negative or plus and plus. And so specifically, when the determinant of these matrices is 1, this is called the special orthogonal group, or SO of n. And so a matrix A that represents a rotation in R squared or R cubed a matrix A represents a rotation of R squared or R cubed if and only if it's part of the special orthogonal group 2 or a special orthogonal group of 3. And the composition of two rotations about R cubed, about the origin, is also a rotation. Basically, this is kind of intuitive. If you rotate twice, you'll get a larger rotation or a smaller one. And this is just because of multiplying two matrices together. And so we introduced a dot product. You guys are probably already familiar with this. I should have probably wrote this out in better notation, but in the textbook he uses capital letters for the vectors, so I just followed that. Another way of writing it is this way. It's the same thing. And so yeah, this is basically just the length of a vector. And so using the law of cosines, we can also write the dot product as the length of x times the length of y times cosine of theta. And this theta angle is the angle between the vectors. And so the angle of theta is pi over 2 when they are orthogonal, or that their dot product is 0. And so I think this should be a proposition, but that's fine. The following conditions on a real n by n matrix A are equivalent, which is that A is orthogonal. Multiplication by A preserves dot product. So AX dot product with AY is the exact same as X times Y for all column vectors. And the columns of A are mutually orthogonal unit vectors. So they're orthogonal with each of the other ones. And a basis that consists of mutually orthogonal unit vectors is called an orthonormal basis. And so orthogonal matrices are actually those where the columns form an orthonormal basis. And that comes from this. And so to prove this proposition, we'll prove A if and only B, and that A if and only C. So starting with A, which is that A is orthogonal, we're going to show that multiplication by A preserves dot product. And so if A is orthogonal, then the transpose of A times A is the identity. And if we consider the dot product, then by definition we can rewrite it like this, which is what we noted before. Back on this slide here, we can write this as transpose times the other column vector. And so we can, there's a rule. Oh, this is a typo. There's a rule being applied here, which is that if we take a transpose, we can, of the product of two, I want to say matrix and vector, we swap places. And I think this is a result that's in linear algebra. Yeah, this should be a to the t, I believe. I don't know why this is a to the a. There's a typo there. And so because this is the identity, this will collapse in on itself, and we'll get exactly this. Yeah. Someone sent a fixed in chat, but yeah, this should be a to the t times a y. Yeah, the a is also missing, yeah. For the reverse direction, which is that we assume that we preserve dot product, and then going towards A being orthogonal, we would suppose that dot product is preserved under A, and then start with this expression here, which we can expand into this from this definition here. And so when we expand this, we get the same kind of result, but we don't know that this is orthogonal yet, so we can't break this down. And so we bring it over to the left-hand side, and we'll pull out x to the t here. And so this product here of x to the t, this thing expression here, and y is 0. Well, one of these has to be 0. And so we must have that this in the middle here is 0 because it has to work for any two column vectors. And the only way that this can be 0 is if A times its transpose is exactly the identity. Why is that? Why is what? Yeah. And to show the other if and only if. Yeah, no, don't apologize. No, you're right. Which I think is the A if and only if C. We let AJ denote the jth column of the matrix A. And so the ij entry of the product, which is this right here, is exactly the dot product of the two columns of A, because they get multiplied together. And so this will hold if and only if the dot product with the same column on A is 1 and 0 otherwise. Yeah. Let me check that actually. A implies C. A is orthogonal. The columns of A are mutually orthogonal unit vectors. Okay. Let AJ denote the jth column. Okay. Oh, okay, I see. It's just an if and only if chain. Yeah, I wrote these a while ago, so. Yeah, we assume that A is orthogonal here, so it's the identity, which can only happen if the diagonal is 1 and everywhere else is 0. So that means that every column has to have length 1, and thus are orthogonal. So the next concept that we cover for this section is rigid motions. And the geometric meaning of multiplication by an orthogonal matrix can be written in terms of rigid motions. And a rigid motion is exactly a map M from Rn to Rn that is distance preserving. So any two column vectors in R of n, the map of x minus the map of y, the distance of that is the same as the distance between those two column vectors. And so the composition of two rigid motions is also a rigid motion. The inverse of a rigid motion is also a rigid motion. So obviously that implies that we're going to have another group. And so we have a group of motions, which we call Mn, specifically rigid motions. And so we follow up with a proposition, which is that if we have a map M from Rn to Rn, then the following are equivalent. That M is a rigid motion that fixes the origin, or that M of 0 is 0. M preserves dot product, so kind of similar to what we said before with the orthogonal matrix. And that M is left multiplication by an orthogonal matrix. That M of x is actually equal to AX, where A is orthogonal. And so I wanted to ask you this corollary from this proposition here, which says that a rigid motion that fixes the origin is a linear operator. And so my question to you is, why is this true? Why is a rigid motion that fixes the origin a linear operator? It doesn't have much to do with rotations. It's relatively straightforward. Like I don't want to say straightforward, but like it's it's nothing complicated, right? If M is a rigid motion that fixes the origin, we know that it's left multiplied by an orthogonal matrix, right? And so if this is true, why is it a linear operator? And there's something here on this page that will help. And it's also something we talked about earlier with left multiplication by a matrix. Yeah, yeah. Yeah, exactly. Yeah. Actually, Mas, you are right. So yeah, the only part is left is the rotation, yeah. Man, I must be a more like I must be tripping right now. Yeah. So the answer I guess wrote a more algebraic answer that, well, if it's a rigid motion, we can write it in terms of orthogonal matrix, and so it's going to be linear. Yeah, and rotations are linear operators. Yeah, exactly. Yeah, the translation part was also something I included. There won't be this vector here. Yeah, we can't have that rotation if it fixes the origin. Or that translation, sorry. And so we'll prove the previous proposition, which is this one right here, using a chain of implications. If we denote M as a map and write M of x equal to x prime, and then M is a rigid motion that fixes 0. We know that M preserves distance, so x prime minus y prime dot product with x prime minus y prime itself will be equal to this expression as well, because these are just the outputs of M of x and M of y. And if we set y equal to 0, because it has to hold for any two column vectors, this yields that M of x dot product with M of x is equal to x times x. So it's length preserving. And so using that fact, we actually expand these two and cancel out any of the products with itself. So if we'll have like an x prime times x prime, it cancels out with x times x. And same with y times y. And so this will yield that x prime times y prime is equal to x times y, which is what we wanted to show. And then if M preserves dot product, we will have that x times the standard basis E of j is equal to this here, which is just M being applied to both components. If we also were to have the condition that M fixes standard basis vectors, we would have that xj, that the column, or sorry, the component xj is equal to x times that standard vector E of j replaced with M of x here. But this is only if M fixes standard basis vectors. And I wrote down here what this implication is. But we don't have this here, that it fixes standard basis vectors. And so if that's true, then it has to be the identity map. So first we suppose that M preserves dot product and consider the images M of each of the standard basis vectors with M. And these are orthonormal. So these dot product with each other, the output is 1 if they're the same and 0 if they're different. And so we let B prime be exactly this ordered set and take the matrix of these columns. And so since this is a matrix of columns that are orthogonal and unit, then it must be that A is orthonormal. And so is A inverse as well by previous results. We talked about like the group of motions before. And so we consider the composition, which is A inverse times M, the map, which fixes each of the basis vectors because of the way that it's constructed. And so this has to be the identity map because of what we showed before, that if we had a map that preserved dot product and fixes each of them, then it has to be the identity. And so M multiplying on both sides would be exactly left multiplication by A, an orthogonal matrix, which is what we wanted to show. What does it mean geometrically that an operator preserves? I believe it's length. I'm not sure about angles. I know it should preserve length. That's a good question. No, you're good. I think the proof is done. I think we like just finished it, so yeah. Oh no, there's one last implication that I want to do as like an exercise. But yeah, that's actually a good question. I actually didn't think about that. I think it's just lengths between vectors, but I could be wrong. It might include angles as well. And so in this proof, we did two of the implications, but we didn't do the last one. So this was A implies B. Sorry, this was B implies C. This was A implies B. This was B implies C. And then we haven't shown that C implies A. So we want to show that if M is a linear operator whose matrix A is orthogonal, then two things are true: that M fixes the origin, and that M is a rigid motion. And so I want you guys to try doing it. I'll prove it in the next slide. I'll show you what the proof is, but yeah, type in the chat, come on the mic. Also, if you're watching this from YouTube, you feel free to pause and try it on your own. I feel like the second part is straightforward if you use this, but the first one is not. You have to use a property for it that we talked about already. So what do you guys think? What do you think for the second one? I feel like the second one is not too bad. Yes. If it's a linear operator, then it is linear, which is really important. So you know that it's defined like this down here, and that's also linear on R of n. I see typing. So yeah, literally. It's literally just that. Yeah. The second one is like a one-liner. It's yeah, it's just m of 0, a times 0 equals 0. So it fixes the origin. The first part is a little bit harder though. And it requires that m is linear and that we preserve dot products with orthogonal matrices. So the linear part comes up like right at the start. If we start with the left hand side, we can pull x minus y into m. And so we get the distance of m of x minus y. And what do you guys think from there? If we pull in m of x minus y. I wish I could draw on this. Are you guys still thinking, by the way, or would you like to see the solution? No, that's okay. That's okay. I tried to make the yeah, no, the notation is here, actually wait. Can you see this? No, you can't. Here, hold on. How about now? You guys see this? So the way to start it is that if we write it, holy shit, like this, and then if m is linear, we can group them like that. Right? And then from there, what do you think we should do? What should we do? Yeah, exactly. It's going to be the distance of a x minus y. And what operation is going on here? Like between these? What operation is that? Because x minus y is just a column vector. Evaluation. What is evaluation? I'm not familiar with the terminology. Yeah, A is just a matrix. This is a matrix. And then these two are column vectors. So what do we think the operation there is? I think there's only one operation. It's actually the one we talked about. Yeah, it's multiplication, but what? Yeah, it's dot product. It's dot product. Right? Oh, okay, I see. Yeah, sorry, I'm not familiar with the evaluation, but I was going for dot product. And if this is dot product here, well, we know that from before that orthogonality preserves dot product. And so this literally vanishes and turns into just the distance between x and y. Yeah, I guess I would. Yeah, matrix multiplication, dot product. Sorry, I think I might have confused the two. This step here. Oh yeah, yeah. I'm so sorry. Yeah, this should be. Yeah, I really hate the notation that I used. Actually, I'm starting to hate it more. But these are just they're just column vectors here, and so when we subtract them, we get another column vector. And so it's just multiplying by, yeah. And so I think I wrote it over here as well. Yeah. Yeah, the notation is so weird. Okay. Okay. We'll move on. We'll move on. There are better exercises. Um, and so before, actually, literally in the chat, someone mentioned translations, and that's exactly the next thing we're going to talk about, which is that rigid motions that don't fix the origin are one, not linear operators, and two, we call them translations. And so any fixed vector b in R of n can be translated, and this is the map that we use as tb of x. It's a rigid motion because it preserves distance as well. So if we take the two and we subtract them, cancels out the b, we get x minus y, and we can just wrap distance vertical lines around it. Yes. Yeah. Yeah, it preserves the dot product. Yeah. Which is the function is the left multiplication by a, your orthogonal matrix. And every rigid motion can be generalized as the composition of an orthogonal linear operator and a translation. And someone else also said this. Um, the person with the mapping profile picture in chat said this as well. And so we can write it as mx equal to ax plus b for some vector b, right? What are we proving? Oh, we're proving this. We're proving that it can be written as that. Oh, man. Let b equal m at 0. Then t of negative b, which is a translation by negative b, at b is also 0, because if we translate by b and by negative b and then plug in b, it will just take us back to the origin. And so this rigid motion fixes the origin, which is also written. Yeah, I wrote it out here. I think there should be an A here. And so we can compose the two and write it as t negative b composed of m at 0. And m at 0 is b, and we know that the translation by negative b at b is 0, so this is also 0. And according to previous propositions, this will end up being the left multiplication by an orthogonal matrix. It was that one proposition we talked about a while ago. And so now we can write this composition, because it's sending 0 to 0, as some orthogonal matrix times the column vector x. And so if we apply t of b, which is the translation by b instead of negative b, we will cancel this translation by negative b and get that m of x is equal to ax plus b. And so b in this case is determined uniquely by what our map m is, and the operator is determined by the map, the negative b translation. This proof is weird. This proof is weird. And so the determinant of an orthogonal matrix is plus or minus 1. We call an orthogonal operator orientation preserving if its determinant is plus 1, and orientation reversing if its determinant is negative 1. And we use the same terminology for rigid motions. They're orientation preserving or orientation reversing if the orthogonal matrix has a determinant 1 or negative 1. And so we can characterize the rotations in r squared and r cubed as the orientation preserving rigid motions that fix the origin, which is a mouthful. And this here is proven in the text, but the proof for it is quite lengthy, and so we won't cover it today because we still have like 2 more sections to go through. So if you want to see it, you can. It's at the end of Artin 4.5. And so now we talk about differential equations as it relates to matrices. And so the solution to an equation, a differential equation, like dx over dt equal to ax, is exactly the set of functions x of t times some arbitrary constant c, e to the at, where a is some real number here. And we can prove this, right, by literally just taking the derivative of this function here. And we see that the derivative equates to 0 for plugging in this function, which can be true only if, they actually multiplied this to the other side and then took the derivative of that and saw that it was 0, which can only be the case if this expression here is equal to some constant. And so if it is some constant, then we can multiply it by e to the negative at. And so that's how we get exactly this function. So they didn't differentiate the function itself. They moved one term over, which is this term right here, and then differentiated it and shown that it was 0. And so we can define two new concepts that we're going to use moving forward, which is a vector valued function x of t and a matrix valued function a of t, where the entries are functions. And so this is how they're written out. Each of these are functions inside here. And so we can now do calculus operations on vectors and matrices because we can apply them component-wise. So taking the limit of a vector would be the limit of all of its component functions. And obviously, certain things like, the limit only exists if all the component limits exist. Those things also hold. And the same thing can be done for derivatives. So we can take the limit, then we can construct a derivative for a vector, which is exactly this. And in particular, we can write out a system of homogeneous first order linear constant coefficient differential equations in matrix form. So we're basically writing out a system of functions, a system of differential equations as a matrix. So like this, which we can write out more clearly like this. It's just a shorter way of writing it. So for example, if we use the matrix 3, 2, 1, 4, we would get the system, the derivative of x1 with respect to t is 3x1 plus 2x2, and the same for the bottom row. And in the simplest and best of cases, we would have a diagonal matrix in which all of the derivatives are literally just one term, right? Like that would be like the best case scenario. And so the solution to that kind of system would literally be this, which is the generalized form of what we saw before. Like we saw it for one case, and then this would be for the system case. And so in general, solving differential equations of this form involves finding eigenvalues and eigenvectors of A. So if V is an eigenvector of A with eigenvalue A, then a general solution to this system is of the form x of t e to the at times eigenvector V. And e to the at is a scalar, and V is a vector. And so here's an example. If we consider the matrix A, which is 2, -1, 1, 3, we let V be an eigenvector 2, -1 of A that has eigenvalue 2, then the derivative of that system will be exactly the solution set of e to the 2t times V, which is this V right here. And that induces this solution right here, this vector. Yeah. And I think in the book they said that this satisfies the derivative of this is the same as multiplying A by this. And this observation allows us to solve this equation whenever the matrix A has distinct real eigenvalues. And in that case, every solution will be a linear combination of the special solutions. And so in order to work this out, we have to diagonalize the matrix in order to get, in order to get the solutions to the more general case. So if we let P be an invertible matrix such that PAP inverse is diagonal, then P equal to the basis of eigenvectors inverse, we define this new matrix here, I think is it? No, this is this column vector, which is P inverse times X hat. And we don't know what X hat is yet. We have no idea of what that is, but we know that the solution can be broken up into P inverse times whatever this X hat is. And so taking the derivative of both sides, we find that this is the case. This is just a regular derivative, and we can plug this back in to our original equation to see that yeah. I'm starting to lose myself here. Hold on. PA. Let me see this. Okay, this slide is kind of weird. I have to check this out again because I'm confused about what I'm referring to here with this original equation. But okay, I'll skip this and I'll take a look back. But the main result of this is that if A is an n by n matrix and P is an invertible matrix such that this holds, such that this is diagonal, with diagonal entries lambda, 1 to n. What is x hat? X hat is some vector here such that when we take that we can break x down the solutions into p inverse and x hat. We don't know what x hat is yet. And part of the result is that we can calculate what x hat is here, each of the components. So part of it is like, in order to find the solution, we have to find what x hat is using the diagonal entries to recover what the solutions are. So we don't know what x hat is. But yeah, this is a main result. Sorry about those last 2 slides. I think there's something like, I must have wrote that at night or something. But this is the main result. So yeah, the main idea is that we want to construct x hat and then multiply it with p inverse. And we will recover the solutions to it. And I'll give an example here. And so if we use the proposition, right, and let p diagonalize a, and then let's say that our a hat here, which is a product, is 5, 0, 0, 2. And p inverse here is 1, 2, 1, negative 1. Then to find x hat, we'll use the lambdas, right, which are the diagonals here, which is 5 and 2, in order to construct x hat. And then using x hat and p inverse, we can get the general solutions to the system. No problem. And so this can be written as a linear combination of basic solutions, C1 and C2. And when the coefficient has distinct eigenvalues, but not all of them are real, the method used can still be applied. The only difference is that we'll have a complex valued function as part of the solution. Also, the coefficients in the solution are arbitrary constants that are usually determined by initial conditions. And so in order to take the derivative of a complex valued function, we break it up into its components, u and v. And we also have, I think this is called de Moivre's rule, which is that we can rewrite this as cosine and sine. And so these are actually really important in order for us to use. Specifically this one right here, we're going to use this. So consider the matrix A, 1, 1, negative 1, and let's say we have the eigenvectors 1i and i1 with corresponding eigenvalues 1 plus I and 1 minus I. And so I would ask you guys to find P inverse and solve the system by finding x hat and recovering x and extracting these two solutions, but we're going a little bit over time. So I'll just run through the solution to this. But if you're watching on YouTube, then pause the video and try it. But P inverse here is literally going to be just the two eigenvectors, which is 1i and i1. And then to solve the system and find x hat, we're going to use P inverse and multiply it by the two eigenvalues. So this is eigenvalue 1, eigenvalue 2, and then we're going to multiply it by P inverse in order to get this system. And when we break it up, it's going to look like this. And we can decompose this using that rule that we talked about, this one right here, into the two solutions, which are down here. And that's all for systems of differential equations. The last is the matrix exponential. And so another way we can solve systems of first order linear constant coefficient differential equations is using matrix exponentials, which has to do with like Taylor series. And so this is the Taylor series for e to the x, and we can replace this with a matrix in the power component here, where A is n by n matrix. And so computing this is actually quite hard in usual cases, but when A is diagonal, things are a lot easier. And even when A is triangular, which we'll see at the end. And so if it is diagonal, we can compute this as literally just the diagonal matrix made up of e to all of these diagonal entries. Basically just raise all of them to e. And it's similar for triangular matrices. But I think there's some caveats to it. There's other values in the top right. And so consider the upper triangular matrix, A, 1, 1, and 2. And here we have that obviously A itself is 1, 1, 2. A squared is this. A cubed is this. And I would also ask you guys to verify the diagonal entries, but I think that will take too long, so we'll just go over them. Same thing applies if you're watching the video. So in order to verify that these diagonal entries are e and e squared, we can just sum a couple of the terms to see that it's the same Taylor series for e to the 1, right? Because we saw e to the x all the way back here. And if we plug in 1, we'll get the same thing when we add up all of the matrices, all of the 1, 1 entries in this equation here, right? This is for the top left entry of A. And so the top left entry will add up to e to the 1. And so the bottom right entry will also have a similar result. It will be e squared once we square the matrices and add them all up component-wise. And the harder part to find out is the top right, which is infinite sum. That's a little complicated, but it can be broken down as e squared minus e here. So this would be the matrix exponential right here. And so diagonal matrices have a really nice property. The exponential of a matrix can be determined whenever we know matrix P such that PAP inverse is diagonal. And we can use this power rule by canceling out all the P and P inverses. And so the same kind of thing can be applied if we use e to the a, the big Taylor series sum that we saw before. A lot of the terms end up grouping or canceling out, and we get e to the PAP inverse. They end up getting grouped together. And so if we assume that this PAP inverse is diagonal with the entries lambda I, then e to the a hat, which is this, is also diagonal with entries lambda I. So this is basically like a rewrite of what we have here. And it would be really nice if we could use the rule of e to the x plus y is equal to e to the x times e to the y, but with matrices instead. But it's not true in general unless a and b commute as matrices. And moreover, we have that the exponential e to the a is invertible for a complex matrix, and the inverse is actually e to the negative a. And that comes from this proposition here, because a and negative a commute. And so because that's the case, we can apply this rule and we'll cancel out and get the identity matrix, showing that it's the inverse. Oh, and this is the Artin exercise I threw at the end. You can try this out if you'd like. It's longer than any exercise I went through in this lecture. And I left some hints here if you would like to try it. We don't have to do it right now, actually. I'm thinking of leaving this, and maybe I'll just go over the solution of it. Or if you want, I can also whatever, I'll go over the solution of it, because I think we've gone on for like an hour and a half almost now. So this is an exercise from Artin, which is that for any matrix A, the determinant of e to the a, the exponential of a, is equal to e to the trace of a. And so this would be really easy to prove if a was diagonal, but we don't have that condition. And so because of that, we have to write it in the Jordan canonical form, which is one of the hints I gave. To rewrite it, this is not right. This should not be D. It's PJP inverse. So yeah, ignore that. And then if you can show that this works for a matrix J, then you're basically done. And you'll see exactly why you're done. So I'll go over the solution real quick just for people that want to watch the video. If you don't want to hear it, you can dip and try it yourself. But I'll just go over it really quickly. So first we would let A be PJP inverse, which is the canonical form of A, where J is a Jordan matrix. And we can rewrite e to the a as P e to the j P inverse, which is something that we did before. We actually did that in the last couple slides here, right? Because J is diagonal, or PJP inverse is diagonal. So if we take the determinant of both sides, we'll get that the determinant of e to the a, which is the same as the determinant of this expression here. And we can break this up and actually cancel out the determinants of p and p inverse here to get that it's equal to the determinant of e to the j. And similarly, the trace of a, we can also rewrite as PJP inverse. And we can reorder this, but you can only reorder this in a certain way, I believe. But we can reorder this in a way that we get that the trace of a is going to be the same as the trace of the Jordan form. And well, if the determinant of e to the a is the same as the determinant of e to the j, and the trace of a is the same as trace of j, if we can show that these two are equal, right, or sorry, that the result holds for these two, then it's going to hold for A because they're exactly the same values. And so that's exactly what we do. Since J is upper triangular, the determinant will also be upper triangular. And so, the determinant of e to the j will also be upper triangular. I should have said that, not the determinant. E to the j will also be upper triangular. And so if we take the determinant of an upper triangular matrix, it is just the product of the diagonal entries, which are j, I here. And similarly, for the trace, the trace of any matrix is just the sum of the diagonal entries, so we just write out exactly what that is as well. Well, since JII, the diagonal entry, is just a number, these two are exactly the same. We can reorder them using that rule that we wish we had for matrices, but since we're working with numbers, we can actually use it. And so these two are exactly the same. And if those are exactly the same, then we can literally write a string of equals to show that this holds true for A. And so that's the proof of this. That's I would say the hard part about it is that you have to look at, one, get the Jordan canonical form, and two, do it for that case because it's equivalent. And so yeah, that's it. That's the whole lecture. Feel free to do any exercises from Artin if you'd like. There are a lot of great exercises like that in there. Some of them are tricky. But thank you for listening. Thank you guys for staying this long. It's been like an hour and a half, which is perfect. I wanted to do just an hour and a half. But yeah, I'll end the recording.